we're going to really start to cover how we regulate enzymes. I find it fascinating. This is just so super cool. I think I get like overly excited about things. You're going to see me just get, this jazzes me up, man. How we turn things on and off. We're going to look, and even more exciting, is we're going to look at the chemistry that goes on in an active site. So we're going to zoom in on an active site and see how those amino acid side chains actually work to catalyze a reaction. So we're going to do some pushing of electrons, and it is just so much fun. So first we're going to start talking about regulation. We're going to focus on the allosteric models. But there are different ways to regulate enzymes. Then we're going to talk about how we identify the amino acids that are at the active site. We're going to look at chymotrypsin, at the chemistry that goes on in chymotrypsin, and look at the reactions. And then we have the other couple things that we're going to talk about. So there's 4 different ways generally that we use to regulate the enzyme activity. Again, we don't want to catalyze all reactions all the time. We need to be able to turn reactions on and off. And so by having an enzyme on the on, we're lowering that activation energy, and we're able to have that reaction go. So let's go through these. I put allosteric regulation at the end because that's what I'm going to spend more time on. The other ones are pretty easy to understand, but be prepared to write a little blurb about each. The way to control by genetic control is through what we call induction or repression. In other words, we're either going to synthesize or not synthesize the enzyme. To cause an enzyme to be synthesized is called enzyme induction. So an example is when E. coli is induced to use lactose as an energy source in the absence of glucose. And so that enzyme to use lactose as the energy source is turned on by genetic control. To cause an enzyme not to be synthesized is enzyme repression. And this is where we are going to inhibit the synthesis of an enzyme by a previous step in the enzyme of a previous step. So a product sort of feedback is a feedback where it causes an enzyme not to be made. So we're talking there's a lot more to this, but we're just basically surface covering this. Compartmentation is just that. Is a physical separation of the enzyme from the substrate. And so this is why we have organelles. So really what we're doing is we're separating the tools and the enzymes that are needed. So here, this is really neat, where we oxidize or break down fatty acids in the mitochondria. We're actually going to study that while we synthesize them in the cytosol. So we don't want the enzymes for both of those reactions to be in the same spot, right? Sometimes what you do is you keep the conditions for the enzymes in a certain spot. So the enzymes will only be active at the right conditions. So lysosomes have a low pH. And so what goes on in them keeps that high proton concentration inside. So you're keeping the tool for the reactions inside the organelle. All right. Covalent modification is pretty neat. Covalent modification is where we can covalently attach a group to turn an enzyme on or off, as in phosphorylation. Here we're showing where we phosphorylate for the attachment. So we're going to use the OH group from these enzymes, or these amino acids, that can attach a phosphate. And sometimes we get the phosphate from an ATP, and that would turn an inactive precursor to an active enzyme. And so what we will do is we'd have the inactive enzyme in a spot where we don't want it to work. And then we bring it to a spot where we want it to do its job, and then we add a phosphate to it and say turn it on. So that's called covalent control. And you can see how the phosphate group can go onto a serine, a tyrosine, a threonine through the OH group. Another way is to remove groups from an enzyme, a protein. This example is a zymogen. So here, what we're going to do in a zymogen is an inactive precursor of an enzyme, where we're going to cleave one or more covalent bonds and transform it into an active enzyme. So chymotrypsin is an example of this. All right, does anybody know what chymotrypsin does? Anybody ever use that? Chymotrypsin chops proteins. It will chop proteins. Actually, I used it when I did something called peptide mapping on a gel electrophoresis or on chromatography, where I wanted to find out where a certain tag was attached. So I had my protein tubulin, huge protein, and I would attach a fluorescent tag on it, something that exhibited fluorescence. And I didn't know where it went. I had an idea what kind of amino acid it would attach to, but I didn't know where it went. So then what I would do is I would treat that tubulin with chymotrypsin, and I knew that chymotrypsin would cleave in certain spots. And we'll talk about chymotrypsin a little bit more later, but it would cleave the protein in certain spots. I could predict where it's going to cleave. So then I would separate those chunks of protein that it cleaved and then find out which one was fluorescent. And I would say, okay, I'm pretty sure that the tag is at this spot on my protein. Does anybody find that interesting? I love that. That was like so cool that I could just add this enzyme and it'd chop it up predictably and reproducibly. And then I would separate it out and then say, and I would use a detector that could detect fluorescence, and I'd say, oh, I know where it is. Yes?
Is it just called trypsin in the lab?
No, chymotrypsin and trypsin are different.
Okay.
And I think later on we're going to talk about it. It's where they are, they'll cleave in different spots.
Okay.
I believe. I got to look that up, but trypsin and chymotrypsin, I believe, are.
I grew cancer cells in the lab and we trypsinized.
Okay.
Just trypsin.
What did you do? So when you grew up the cancer cells, did you isolate a protein from the cancer cells?
No, we tried to isolate different,
So different molecules from the.
different RNAs, yeah.
Oh, RNAs?
Yeah.
Okay. And then you cleaved it up to see if the RNase was a little bit different? Is that what?
Yeah.
Yeah. Yeah, it will. You would choose a different one based on. I used chymotrypsin and trypsin in my experiments, but that was a long time ago, so I could be wrong. So that's something for me to look, or us to look up, what the difference is between them. All right. So chymotrypsinogen is the zymogen. That is synthesized and stored in the pancreas. Do we want your pancreas to be chopped up? No, we really don't want your pancreas to be chopped up. So we keep it inactive. And then what we do is we secrete it into your small intestine. And, oh, there we go. The digestive enzyme trypsin cleaves it. All right? And that cleaves it to give what we call pi-chymotrypsin. Pi-chymotrypsin. Then pi-chymotrypsin cleaves itself and gives the active alpha-chymotrypsin. And so what happens, I think the blue is chymotrypsin and the pink is chymotrypsinogen. And so what happens is They identify one of the amino acids, actually a couple of them, and isoleucine and aspartate. And you can see the isoleucine changes in its spatial, in space. It's moved, where the aspartate really hasn't. But it's changing. You can see there's an overlay, and it's changed where the primary. So it's changing the primary structure in covalent control. It's changing the primary structure, and because you're changing the primary, you change, of course, the secondary and tertiary as well. So this is what we see. So this is our amino acid chain, 245 amino acids in chymotrypsinogen. And trypsin cleaves at a certain spot. These yellow things are disulfide bonds. So it cleaves after this arginine that's at 15. So it's cleaved, but it's still attached. It's not like we're getting rid of part of it. It's still attached by disulfide bond, but it's a different unit. Then what we do is it chews its toes off. I mean, basically, that's really what it's doing. It's self-digesting. So you can, like, it's biting off its big toe, into both of its big toes, all right? And right here, the 14 and 15 and 147, 148, they're chewing those off, getting rid of those. And this is our active enzyme. Notice that there's 3 different peptide chains held together by disulfide bonds. And this is our active chymotrypsin. How cool is that? So this is non-active, and this is active. And so we have this in our pancreas. We don't want to have it chopping up proteins. Not good. We wouldn't have a pancreas then. And this is where the active enzyme in our small intestine is going to work. All right, let's talk about the way we're going to basically spend the rest of this semester on allosteric control. Allosteric control of an enzyme results in the binding of a substrate. Allosteric enzymes are enzymes that are composed of more than one subunit. So in order to be an allosteric enzyme, you have to have more than one subunit. It has to have a quaternary structure. And S, A, and I. S is the substrate, A is an activator, and I is an inhibitor. And all of those are going to change the quaternary structure. All of them are allosteric effectors. They can be inhibitors or activators. Oftentimes, you'll see an inhibitor be a downstream product. So what I'm showing here is a pathway. A pathway is just a series of reactions, each catalyzed by an enzyme. Some enzymes are under control. Some enzymes aren't. They're just driven by, whether they go forward or not, by Le Chatelier's principle. You guys remember Le Chatelier's principle? Does anybody need me to remind them what Le Chatelier's is? Okay, so Le Chatelier's means if you increase the concentration, you have a reaction at equilibrium. That means it goes both ways. And so whether it goes from reactants to products or products to reactants depends on the concentrations. And so if you have more than what you should at equilibrium of the reactants, then it's going to go forward. If you have more than what you should of the products at equilibrium, then it's going to go in the reverse direction. So many of our pathway reactions are driven by Le Chatelier's principle, that if we start building up the reactants, it's going to go forward. If we have plenty of the products around, it's not going to go forward. However, a lot of, especially the first reaction in a pathway, will be under allosteric control, where a final product will inhibit an earlier reaction. And that's called feedback inhibition. And so it makes sense. If we have a lot of our final product, do we need the pathway to proceed? No. We don't want to accumulate a lot of things. Your cell is very, very efficient. All right? We're not going to have reactions going that we don't need to have going. We're going to conserve our energy. So, and actually, another way is a feed-forward mechanism, where if we have, say, from a different pathway, a lot of the reactants building up, then that might activate our enzyme. So as we're studying our pathways, we're going to spend a lot of time talking about those enzymes that are under control, why they're under the control, and what is going to be those controlling molecules and why they would be those controlling molecules. So I mentioned before, ATCases are an example of an allosteric enzyme. Our velocity versus substrate concentration plot shows sigmoidal shape. Remember I said the hard binding, meaning the substrate is binding to that first subunit. Once that substrate is into that first subunit, it changes the conformation of the other subunits so that it is easier for the other substrates to go in there. And up at the top, we've saturated our enzyme. So here we show the effect of an activator and an inhibitor. So you can see an inhibitor makes it harder to bind. An activator makes it more a hyperbolic shape. Makes it all simple binding. Makes it all what I call easy binding. Remember I said hard or easy binding? Depends on how many times, here's my substrate, here's my enzyme. If it's hard binding, maybe you need more than one collision for that substrate to make that enzyme-substrate complex. If it's easy binding, it's going to go right in. So here, inhibitor plus it's the product of the reaction plus the ATCase is going to be slowing down the reaction. You need, in order to have the same rate, you need a higher substrate concentration. Our control, no ATP, or that's an activator, or CTP. That's our inhibitor. It's normal sigmoidal shape. And what you're losing with an activator is that hard binding. It becomes all the easy binding. ATCase is sort of a weird enzyme. Of course, it's not colored like this. But we have the trimers. There's 6 here. There's 3 on the top and 3 on the bottom here. Those do the catalysis. And then we have the regulatory dimers on the outside. And we can actually use detergents to get rid of these regulatory units. And the shape of the binding curve goes from sigmoidal to hyperbolic. There's no more hard binding if we remove these regulatory dimers. I think that's pretty neat. All right, so here's where the weird stuff comes in. Since these allosteric enzymes can't be explained by the Michaelis-Menten model, we can't use the terms competitive and non-competitive. So we're going to have parallel terms. We're going to use a term that is parallel to Km. We call it the K.5. It means the same thing. It's just going to be a different term because the Michaelis-Menten is for non-allosteric enzymes. And that you can't have a Michaelis constant if the Michaelis model is not going to be valid. So it's the same concept. It's meaning the affinity of the enzyme for the substrate. But instead of calling it Km, we call it K.5. And we can't use competitive and non-competitive terms. We're going to use K and V systems. It's more complicated than what I'm going to say, but and for that we are not studying the math. But they are parallel. All right, so the K system effectors change the affinity of the enzyme for the substrate. It doesn't change the shape of the curve, just the position. In V system, the enzyme has the same affinity for the substrate, but the rate has changed. So So it's the same thing. Which one changed our Michaelis constant for the non-allosteric? Competitive. So that's like our K system. Which one changed our Vmax? Non-competitive. So that's like our V system. So there's different terms. They're parallel. Math is very different. I'm not even going to go there, but this is, they're parallel terms. Okay, so all these inhibitors or activators are called effectors. A homotropic effector is the substrate molecule itself. So binding one aspartate affects the binding of others. A heterotropic effector is when different molecules, not the substrate, causes either an activation or an inhibition. We can explain the kinetic properties of allosteric enzymes by describing the conformational change between a highly active, or what we call relaxed state, or low activity, or tense state, or tight state. So this is, when I said hard binding and easy binding, the relaxed state is what I call easy binding. The tense, taut, or tight, that is the hard binding. That's the inactive form, or less active form. And we have two models, the concerted and sequential models. The concerted model says that there's an equilibrium between these two forms. But at the beginning, almost all of our enzyme molecules are in this hard binding or inactive tight form, taut form. And what happens is, in the presence of the substrate, we're going to shift the equilibrium from the taut form to the relaxed form so that we can get an all at once, all the subunits at once. We get our easy binding or active form. So all changes are concerted. So in all subunits, it's happening all at once. So here we have our relaxed and our taut states. Our substrates can bind into these little square things. And so here, relaxed, it's the square thingy is, the active site is nice and open, easy to bind. You can see here in the taut state, the conformation is not so easy to bind. And so here, at the beginning, without substrate around, we have an equilibrium where the equilibrium lies towards the product, towards the taut state. So this L, this equilibrium constant, is very large. We're much more taut than relaxed. What happens is, when substrate comes along, and so say we have 100 enzymes, 99 of them are in the taut state, only one of them is in our relaxed state. That one that's in the relaxed state binds the substrate. It pulls it out of our equilibrium. What's going to happen? If we pull, remember Le Chatelier's principle, if we pull this out, how is this going to shift? It's going to go towards our reactants more, and we're going to shift more. So then that one is out. Now we're going to go down to 98 and pull that other one over. And then that will bind the substrate and pull that one out. Then we're down to 97. Pull that one out and bind another substrate. All right? The big idea here is that we are, the equilibrium between the relaxed and taut is that you don't have one side turning from taut to relaxed, and then that induces a conformational change in the other subunit. The enzyme is either all taut or all relaxed. That's the basis of this model. So let's talk about this equilibrium constant. This equilibrium constant is large, meaning that there's more product than there is reactant. There's more taut state than there is relaxed state. It does explain the sigmoidal effect. So let's take a look. Again, I have another very busy slide. So here, this is substrate concentration, and here is I guess, rate here. Yes, of course, it's rate. And so here, and we have Vmax up here. Let's just take a look at the left-hand side. The left-hand side is talking about the equilibrium constant. A larger equilibrium constant means that we will favor products. So this L of 10,000 is much larger than this L of 1. L of 1 means that we have equal amounts of our products and reactants, right? It's constant. An equilibrium constant is concentration of the products over the reactants. So if an L is 1, then we have equal amounts of the taut and relaxed state. So really, if you notice the shape of the pink, there is no hard binding because there's plenty of our enzymes that are easy binding, the relaxed state. But as you get bigger and bigger with this equilibrium constant, you're shifting it to more of the taut state so that you have hardly any relaxed state around. So we can describe the sigmoidal shape of our allosteric enzyme with this equilibrium constant. You have more sigmoidal shape is a larger equilibrium constant, thus a higher concentration of our taut than relaxed. Over here on the right, we're talking about a C term or a cooperativity term. And this is where a lower value means that there is more cooperativity between the substrate and the relaxed state than the substrate and the taut state. A high C, which is this 0.1 here, relative to basically nothing, means that there's no difference in the substrate affinity for relaxed or taut. So it's not sigmoidal. So that the substrate, this higher C, means that the substrate likes both the taut and relaxed. But if you can see in the blue, the lower C means that the substrate likes the relaxed a lot more than the taut. So as you increase the C, or cooperativity term, you're losing that sigmoidal shape, meaning that there's really no difference between the taut and the relaxed. Okay, next we're going to talk about what does having an activator or an inhibitor do. This is, again, it's kind of busy, but I really, really, really like it. Okay, so I talked about my fish with Le Chatelier's principle, right? Did I talk about my fish? Okay, let's talk about my fish. My fish, we had several years ago. We had beta fish. And those of you that had general chemistry with me remember this story, because what happens if you put two beta fish in the same fish tank? They eat each other alive, right? So you cannot have them in the same fish tank. But we did. But what we did is we put a plastic piece in between so the water could get across, but not the fish would just ram that plastic piece to try to get at each other. What a nasty pet, right? I don't know. Now we've evolved to 2 cats and 1 dog, but you know, it's okay. All right, so imagine the left-hand side is the reactant side, and the right-hand side is the product side of my fish tank. And here in the fish tank, equilibrium is equal concentrations of water on both sides. Now, we know equilibrium is not equal concentrations. It's equal what? Equal rate going back and forth. But let's just say in this one reaction, the equal concentrations are equilibrium. What would happen if I scooped out the reactants?
Water
would go back to the reactants, right? What if we scooped out the products? It would go, water would flow this way until equilibrium was attained again. What if I added in more reactants? It would go that way. Okay? So all of the Le Chatelier's principle can be described by Dr. Barron's fish tank. We're not shopping anymore. We're using a fish tank. Okay, so this is the reactant side of my fish tank, and this is the product side of my fish tank. Okay? Fish tank right, fish tank left. And down here, it's scooping out. Okay? Down here, and over here is scooping out. So the entire fish tank is just this part, the RO and the TO. Okay? Now, what happens is in the concerted model, what happens is either binding the substrate or binding an activator will scoop out reactant or relaxed state. But it will scoop it out, but it's still available because it has another subunit to bind to. So we're scooping out. So what does it do to the fish tank? If I'm scooping out over here, what's it doing? I'm going to go from product. If I'm scooping out over here, I'm going to have more product come back, right? So here, our tot is going to get less. We're going to have more and more and more reactant until we have all reactant. And if I have more substrate binding and more activator binding, that is just going to be pulling the relaxed state out. So this blue is normal without an activator or inhibitor, okay? If I add in an activator, what is it doing? It's taking that hard binding out. It's moving this equilibrium so that the tot is making more relaxed until we have only relaxed, and then see the hard binding is gone. Now, if we add an inhibitor, it's going to scoop out on our product side. It's going to scoop out there and shift the equilibrium so that relaxed makes more tot, right? And then it's going to take it out. So then it's not available. So what's happening, compare the blue to the green, when you have more, when you add an inhibitor, it's going to make it more or all hard binding. Do you see that? It's all or a lot more hard binding. So an activator increases the amount of easy binding or relaxed state. An inhibitor increases the amount of taut or hard binding. An activator increases the amount of relaxed or easy binding by removing it from that equilibrium. And an inhibitor increases the amount of taut or hard binding by removing it from that equilibrium. What is happening to the K.5? The K.5, which is analogous to our Michaelis constant, means that a low K.5 means high affinity. So look at what's happening at the half of Vmax, or maximum rate. We are measuring our K.5. When you add an activator, what's happening to it? It's getting smaller, right? So you're increasing the affinity. When you add an inhibitor, the K.5 is getting bigger. So you're decreasing the affinity.
Does tot mean a product?
No, tot is the conformation of the enzyme where it takes more than one collision in order for, it's not easy binding. It takes more than one collision. So it's the form of relaxed and taut is how easy or what affinity does the enzyme have for the substrate. Will it take it in easy and form that enzyme substrate complex easy? Or does it take a lot of collisions to take it in? So the taut is an inactive form. It's not really going to make the product. Where the relaxed is the active form, where it's easily going to make the product. So there's two different things. There's an equilibrium between the two forms of the enzymes. I'm not talking about the reaction that it catalyzes. I'm talking about the equilibrium between the active and the inactive enzyme. Okay, the other model of the allosteric control is the sequential model. And this has actually been called a more accurate model of behavior, and we'll talk about why in a second. So what they say is that we start all out in the taut form. It's all in the taut form, the enzyme, the hard binding. Then the substrate actually binds to the taut form, and that binding changes that subunit to the relaxed. Once that one subunit changes to the relaxed form, it changes the conformation of the other subunits. Now this one is better because it matches our induced fit model of binding. Can you imagine, all right, so say this is the taut form active site, and I'm trying to put a square piece, or maybe it looks like this. I'm trying to put a circle substrate in, right? The substrate is circled, but it's not really matching that, right? So what's happening is it takes a couple times for that circle to come in to my active site. And once it does, it changes to the circle, complementary. And that physical movement, that induced fit, that coming together from those electrostatic attractions between the active site and the substrate, or any kind of interactions, is an actual physical movement, like we saw with hemoglobin. And that movement causes movement in other parts and other subunits. And then it makes the other subunits have that circle form instead of the V form, right? So it's a little bit different. So it does do a better job modeling cooperativity. So this is the idea. Here, we actually do bind to taut, but it takes a couple collisions. See how, okay, we're putting a square, or I don't know what kind of shape that is, into a circle. So here, this is a different form. We have a semicircle active site, but we're trying to put something that's square into it. Let's just call that square, because I don't know what kind of shape that is. And so once it's in there, by induced fit, remember the Venus flytrap, that's the induced fit, not lock and key. But by the induced fit, it fits in there, it changes this side to relaxed. And once this side's relaxed, it changed that conformation, it's going to change the other one. So it's sequential, not an equilibrium between all taut and all relaxed, but that we are actually binding to the taut. Now, this does a better job of understanding our negative cooperativity, that's hard to say, where we're binding an inhibitor, and the inhibitor sort of locks that taut form. It locks it in place so that they're all the lower affinity. It doesn't allow your conformation to change from taut to relaxed.